Hi everyone, and this is Formation Equations. So far we have two methods, and we're going to add a third method of how do we find enthalpy. We know we can use our calorimetry equation, we can do Hess's law, and now we're going to be able to do formation equations. In today's lesson, we are going to learn how to make our own equations using something called formation equations. And then we're going to use these formation equations to do a Hess's law in our last step. And that's going to allow us to solve for the delta H that we're looking for. Each ingredient in the balanced equation needs its own formation equation, except for elements that are in their stable state. So here are the steps for making our own formation equations, and it's very important that in our first stage that we follow these instructions to the letter to make sure we have proper formation equations. That's stage one. In stage two, then we'll move on to Hess's law, which we already know how to do. So let's review these steps. Step one, we're going to write the compound that we want to make the formation equation for to the right of the arrow. In step two, we're going to write reactants as elements in their stable state at SATP. This is basically just room temperature. Don't forget about our Hofbrinkels. So if I have an element that is one of the Hofbrinkels, instead of just a regular plain O, for instance, it is an O2. All of my Hofbrinkels are diatomic, meaning they all have 2. These elements will go to the left of the arrow because they will be the reactants that I'm making that I'm forming my compound from. In step three, I have to balance for 1 mole of product. All balancing is done on the reactant side or the left side of the arrow, and this is really important because if I don't do this, I can't go to step 4. Step 4, I can solve for the delta H for my particular reactions by looking on page 799 and 800, but these values are per 1 mole. So if I don't balance for 1 mole of product, I can't look up delta HF values. F just stands for formation. And if I can't look up what delta H is, I can't solve the problem. So that is an issue. So that's stage one. Follow these 4 reactions, or 4 rules rather. Let's just practice using those rules right now. I want to make a formation equation for methanol. I'm going to start by figuring out what the heck is the formula for methanol. And again, a really good place to look is that table that we're going to end up using anyways, that is on page 799 and 800. So in step 1, it tells me that I want to write the formula that I'm trying to make as a product. So I'm going to put my arrow in, and then I'm going to put my formula, CH3OH, as a product. That's step 1. Step 2 tells me I'm going to put my elements to the left-hand side, the elements that make up this compound. So if I look at my compound, it's made up of carbons. That's just a regular C. That's not a Hofbrinkel, so no 2. That would be a solid at room temperature. Then I've got some hydrogens. That is a Hofbrinkel, so it's going to be an H2. That would be a gas at room temperature. And then I have some oxygen. That is a Hofbrinkel, so it's going to be an O2 and a gas at room temperature. Then I'm going to balance for 1 mole of product. So again, my carbons, I have 1 on each side, so that's good. My hydrogens, I have 4 on the right, so I'm going to put a 2 in front to make 4 on the left. And my oxygens, I have 1 on the right. I'm going to use a half here to put just 1 on the left. Notice that I've tucked that arrow right next to my product, and this is to remind me that when I balance a formation equation, again, it has to be for 1 mole of product. Therefore, I'm not allowed to put a coefficient here, even if I want one. I can take care of that with Hess's law. All right, the last step is to look up that value in the back of the book. So this is a delta HF, which is a delta HX, which means per mole, but we've replaced F for X to say what kind of reaction it is, and in this case, a formation reaction. So let's look up methanol and come up with a value. I looked on page 800 to find this one. You'll notice the table is in alphabetical order by name, but if you don't know the name of something, you can also look by formula, so it's very convenient that way. And the value here is negative 239.1 kilojoules per mole. So typical questions are going to require multiple formation equations, and these now become our known equations, and that is stage 1. Let's call that stage 1. And then once I've done my formation equations using my 4 rules, don't skip the rules here, then I can move on to stage 2. Stage 2 is that Hess's law, where I can use my manipulations, either flipping or multiplying and dividing, to make those formation equations that I just made to match my target equation. So let's put the two steps together now. So we're going to use formation equations to find the enthalpy for the following equation. I'm just going to put my arrow in here. And you do have a handout on the website that you can use to fill in underneath if you like, or you can just do it on a piece of lined paper. We're going to do it together now. So the first one that I'm going to make is the NO2. I'm just going to go in order from left to right. I am going to shift the arrow just a little bit to give me more space though. So NO2 gas. So again, I'm going to go through my 4 steps for making formation equations every time I need to make one. So I'm making an NO2. Notice that in the balanced equation at the top, there is a 2 there, but remember the rule about formation equations is I have to measure it for 1 mole of product, so I'm not allowed to bring that 2 just yet. That will happen in stage 2, which is when I do my Hess's law. So following our rules for formation equations. So now I'm on to step 2 where I'm going to put the elements that make up my product. So I've got N2, again a Hofbrinkel, and I've got O2, again a Hofbrinkel. Then I'm going to balance, and all balancing happens on the left-hand side because again, I need to balance for 1 mole of product. So I'm going to need a half in front of the N2. And lastly, I'm going to look up the delta HF value in the page 799-800. And when I look it up, it's positive 33.2 kilojoules per mole. All right, on to the second reaction. The second ingredient in my target equation here is water in the gas form. So again, I'm balancing for 1 mole of water at the end, so I'm going to tuck that arrow in nice and tight, and I'm working on the left-hand side now. So what are the reactants that make water? They are H2, a Hofbrinkel, and oopsies, and O2. Again, balancing for 1 mole of product, H2 is fine. I'm going to put a half in front of the O2, and again, I'm going to look up my delta HF value. Now, water, you'll notice, actually has more than one state and more than one delta HF. So you do have to be mindful of the state here. We want the water vapor or gas version, not the water liquid version. The third ingredient, or the first product, is oxygen. But oxygen is an element, and we don't make elements from anything other than elements. So we can skip that one and go on to the last ingredient, which is the last product here. And we're going to make that N2H4 gas. Again, our reactants here are the elements that it's made from, so N2 and H2. And in terms of balancing, we're going to need a 2 in front of that H2. So let's have a look at the delta HF. Again, if you're not sure what to call this thing, look it up by formula. This is another one that has 2 possible states, so you do have to be mindful that you choose the correct one, in this case, the gas. All right, stage 1 complete, folks. We're now into stage 2. We're now going to use our Hess's law to figure out how to get these equations to match the target. The nice thing about when we do formation equations, we already know which element to look, or what compound to look at. It's the one in the products, because that was the focal point for making each of these equations. So by looking at NO2 in that first equation, I can see that I need to flip and multiply by 2 to make it match the target. Again, what I do to the equation, I also have to do the delta H. The water is the second key ingredient here. Again, looking at the target equation, I have to flip and I have to multiply by 2. And the last equation, my key is the N2H4, and it's already on the product side and no coefficient is needed. So I'm just going to leave that one exactly as it is. All right, let's do the manipulations now. So I'm going to flip in times 2. At this point, I'm just going to drop the states because they're not really important anymore. I'm going to come back and do the delta H's afterwards. 2 waters, 2 H2s, 1 O2, and finally N2 plus 2 H2s makes N2H4. All right, I'm going to pause and work out those delta H's. The one thing that's important to note here is when we manipulate them, so when I multiply them by something, flip them around, they're no longer formation equations, and therefore they're no longer per mole either. So in the section here, you'll notice that I've got regular delta H's now and just kilojoules. So I've dropped the per mole and I've dropped the F to show those changes that I've made. So let's see what we can get rid of on both sides of the equation here. I can get rid of N's, I can get rid of H's, I can add my O's up, and let's see what my target equation is, whether it's a match or not. So I've got 2NO2 plus 2H2O, making N2H4 plus 3O2, and it is a match to the target equation, therefore I can go ahead and solve my delta H. Getting positive 512.6 kilojoules here. Let's do a part B to this same question, and this time I'm looking to find out what would be the enthalpy of 14.6 grams of nitrogen dioxide, which is this ingredient, in the above reaction, above meaning the previous slide. So I'm looking for delta H for 14.6 grams. So I'm going to use my delta H equals N delta HX equation. So I need to find N and I need to find delta H. Let's start with the N. So I have 14.6 grams, so I'm going to do my mole conversion. So moles is equal to 14.6 grams times 1 mole. And let's find the molar mass of NO2. About 46 grams for the molar mass, giving us 0.3174 or so for the moles. In terms of the delta HX piece, I know that 2 NO2s makes 512.6 kilojoules worth of energy. So I'm going to do a little side action over here, and this time I'm going to use my positive 512.6 kilojoules divided by my coefficient 2 moles, since those two pieces of information go together, and that will allow me to find my delta HX. Alright, I've got all the pieces that I need, so let's put it all together. So delta H equals then my moles. Can't seem to make dots today. There we go. Times my delta HX. My moles will cancel. And here we should get positive 81.3 kilojoules, maintaining 3 significant digits based on the 14.6 given in the question. Alright, this is a second example here, and I want you to pause the video and try this one on your own first, and then press play to go ahead and see if you are correct. So go ahead and pause now, and I'll start taking it up on the next slide. Alright, so let's go ahead and start making our formation equations. I'm going to start with the first ingredient. I'm just going to move my arrows over to give me a little more space. So we're going to start with NH3. And again, we're balancing, or we're creating elements on the left. So N2 in the gas form plus H2. Both are Hofbrinkels. For balancing, I'm going to need a half N2 and 3/2 H2. Again, I cannot put a coefficient in front of the NH3 just yet because these are formation equations and they're always for 1 mole. Because of course the next thing I have to do is I have to look up my delta HF, and that's a per 1 mole. So if I don't have per 1 mole of NH3, I cannot look it up. I looked it up and it's negative 45.9 kilojoules per mole. The second reactant is O2, so it is already an element. We don't have a reaction there. So let's go over to the next one, which is NO. And we do have a reaction there. So we have N2 gas as one of our ingredients and O2 gas, both Hofbrinkels. And then balancing, we need a half of each. And let's go ahead and use page 799-800 to look up that delta HF. And our value here is 90.2 kilojoules per mole. And the last ingredient is the water, H2O in the gas phase. It's made of H2 gas and O2 gas. And we need a half in front of the O2. So again, looking at that value for water in the vapor phase, getting negative 241.8 kilojoules per mole. So now we're ready, that's stage 1 complete. Let's do our stage 2. We're going to do Hess's law, and the focal point is the products. So we're looking to see how do we manipulate each one to match the target. So the NH3 has to be flipped, and we have to get a coefficient of 4, so multiply by 4. And reaction number 2, we're focusing on that NO. It's on the correct side of the arrow, but we do need a 4 coefficient, so we're going to multiply by 4. Water, same thing. It's on the correct side of the equation, but we do need a coefficient of 6. So we're going to multiply by 6. So I'm going to go ahead and do those manipulations. We'll see how it turns out. All right, so I've just done my manipulations to both the equations and the enthalpy. Now I'm going to do my cancellations. So I can get rid of N2, I can get rid of H2, and I can add up my oxygen. Notice when I worked with my enthalpies, I dropped the F and the per mole once again. And let's see what we've got. So on the left, we've got 4 NH3s and 5 oxygens. And on the right, we've got 4 NOs plus 6 H2Os. And if I compare that with my target, it is a match, so I can go ahead and add up my delta H's, and they're negative 906.4 kilojoules. So let's do our part B. We want to know what is the enthalpy if we have 2.6 grams of water for the equation that we just worked with. So my water here is 6 waters making negative 906.4 kilojoules. So I'm working with that same equation, delta H equals N delta HX, and I have 2 pieces to do first. So let's do our moles, 2.6 grams times 1 mole over molar mass of water is about 18 grams. About 0.1444 moles there. And then my delta HX, remember, I'm going to be doing a little side action here for my delta HX. My delta HX is going to be my delta H, negative 906.4 kilojoules divided by 6 moles, again from the balanced equation, negative 151.1 kilojoules per mole. And then let's put it all together. So delta H then equals my moles times my delta HX. My moles will cancel with negative 21.8 kilojoules. Your homework can be found on the worksheet on the website. Have fun!